that's not on the PowerPoint is on our generators. I don't have a full one in here, but on our generators that have brushes on them, here we are. This one is a bad example of what I want to teach you. So why grab it, Case? Because all those brushes are pretty much straight on, right? They're not on an angle, the brush holders are straight, but if you're using that generator test bench out there and you look inside at the brushes on most of the ones you guys are rebuilding, the Delco Remis, there's a direction kind of to the brushes where they're tipped, right? So normally, if you're working on an aircraft, the best way to say, hey, what way is this thing rotating, is you have the generator on the aircraft and you look at the prop and say the prop's going this way, the belt's going, okay, and you can figure it out. But just for your test bench situations, if, we'll call this the brush, this is the brush. If this is the brush, and here is our armature, we'll make it big, and here's our armature. A lot of them are tipped a little bit in the holder, and the idea on most of them is they're going to be going around the way that you would shovel your driveway. So you're going to shovel it in that. It's essentially going to kind of force the edge into the driveway. That helps keep it, I don't want to say sharp, but it keeps it wore the right way and whatnot. So if you're looking at them, it does go the direction that you would shovel the driveway. If I went the opposite direction, like if you had a shovel and you were dragging backwards, you know how all the snow, well, Bednago wouldn't know. Have you ever shoveled snow? Yeah. It's fun. I like it. Good exercise. But if you drag it backwards, it's the same with dirt and a shovel. Have you ever shoveled dirt? We got to get you a shovel. Yeah. If you go backwards, you know how it kind of just flattens out under it and it doesn't scoop up into your shovel. So when you're looking at the generator test bench, if you can't figure out, do I need this clockwise or counterclockwise, be thinking, hey, it's slightly the way that it's kind of tipped in so that I'd be scraping the stuff off the armature. So for lack of a better way to explain it, that works. If you want to go out there and have me point that out to you, I'm happy to do it. But that was really giving me grief trying to figure out which way is this supposed to go. And it helps. Worst case scenario, you just reverse it, right? Try it the other way, but that's a good way to know it. All right. Ooh, nice. This is actually one of the aircraft here at SMAT. No, it's not. That's not a SMAT one. The next one is. So over here, that's our magneto switches. So we're going to go over magneto switches today. And pretty fancy labeling. Start on left mag. And that's pretty common. So very often when we're starting our aircraft, we have the right magneto shut off, meaning we're not using it. And we're going to go over today how that means that we ground it out. So they're going to say when you're starting this old aircraft, only have the left mag on, don't have the right mag on. So they've got two individual switches. That's pretty old school. So if I upgrade it just a little bit, this is the Citabria at SMAT. This sits, this one here. And on the Citabria at SMAT, it's got a very similar situation to this, where we've got ignition left, ignition right, and you've got to decide individually which switch you're going to have on or which switch you're going to have off. And remember, on these old style, if I turn the ignition switch off, it's actually closing the switch. It's making the connection to finish a circuit. So ignition switches are backwards on a wiring diagram to what you'd expect. We're going to go over that today. Well, when we say ignition switch, it's like, why are you using the word ignition, Case? Ignition, ignite, means lighting fuel. And that's why, is ignition is lighting our fuel, it's our magnetos. So we're going to have a separate switch, unless you're really good at hand propping, which, you guys, did you get to hand prop yet? Or is it, yeah, okay. I've never actually hand propped an airplane we're going to fly. It's on my bucket list. Go hand prop one and then fly it. Just feels like that'd be a little more pure So, we're all lazy nowadays, us 21st century people. We need a start button. So, does this one have a start button? I don't see a start button. On SMAT's Citabria, the start button is right here. So in order to start this aircraft, it's similar. I'm just gonna kick the left mag on, do whatever I gotta do to prime it, and then I'm gonna push my start button in. These are the easiest wiring diagrams to understand and figure out because it's 3 separate switches, left mag, right mag, start button. And then the company started combining them in a little panel. So we would have left mag, right mag, start button. Well, okay, we're getting pretty cool. And then we get to the point where they say, you know what, we can just put both switches in one switch. So this one, obviously a little old, this has both the left mag and the right mag switch in here. So we've got off, left, right, and both. So inside of the box, we got one, we'll call it the left switch, one, we'll call it the right switch, and they just tie together a common terminal on the back side. And this would end up going out to the mag, whoa, there's an A in mag. And we're not going to cover how a magneto works until we get to power plant class. But remember, when the switch is closed, it says no spark. I don't want spark from you. Make sure you're all paying attention. Oh, there he is, Harrison. I was going to say, I've been staring at you in the top of the cup. So in this position with them both open like that, am I set on off, left, right, or both, Harrison? Yeah, we're set on both. Good job. Because they're both up. Okay. So if I were to turn the right switch down to being closed, now what position would I be in, Timothy Peterson? I didn't take attendance. Sad that reminds me, Tim. Say what? Alright. I have a off, left, right, or both. I don't have an on. So you gotta pick one of those. Left. Alright, so left is on right now. So that is correct. Right is off. So this switch would be in the left position right now. Making sense to everybody? Cool. So that means if I switched it over to that, this should be an easy one to give me. Low-hanging fruit, Corbin. Give you an easy one. Right, that's right. And did we do that one yet? Last but not least, Josh. Uh-oh.
Yeah, Dan's trying to explain this to me.
Alright, so I have both switches closed now, so am I in the off, left, right, or both position?
Off. I just can't figure out how you're getting power to the.
Oh, that's the problem, we're not getting power anywhere. So the way it works, the long version is if I have that closed, this in an aircraft hooks up to ground over on this side. If I have it closed and hooked up to ground, I basically ruin my spark making generator. We go, nah, we're not gonna let you make spark. That's the short version of how it works. So the simplified version, the way to think of it would be, if this guy was going to make electricity and there's a gap right there that we normally want a spark to jump through, and I close that switch, is the spark gonna jump through this gap? No, it's just gonna go through that wire, right? Alright, so that's the very dumbed down, simplified version of how a magneto works. That's basically what it is, but it gets gets a bit more complicated, and we're not gonna go there today. So think of it that way for now, and you're fairly accurate, is our spark making device normally is gonna make a spark that jumps across the thing to ground, but if we close the magneto switch, it's gonna say, well, I'm not gonna send the spark across there, we'll just send the power through the wire that's closed, and we're not gonna do it. Corbett? It's pretty much short to ground. Like I said, we'll go over it more in PowerPoint. The reality is, instead of just a gap, what ends up happening is this is actually a coil, and then there's a transformer with a crazy high step-up transformer, and that's the one that has the spark to ground. And what we do is we short out the primary coil so that no power goes through this one, and if no power goes through this one, it's not gonna do a stepped up voltage to go to that one and give us a really hot spark. So, you guys made me do it. Lesson 101 in magnetos. So that's why when we close it, basically I'm not sending power to my transformer. If you're a car guy, I'm not sending power to my coil pack to make a spark. Because why would it wanna go through there? It'll just go through our switch to ground and kills the system. So yeah. Thinking electricity, you're like, you can't do that, you're gonna fry something, right? You just shorted it out, but yeah, we shorted it out, and we'll get to later why we don't really care on these. This is not a constant power source. Constant. All right. So ground off the common one, right. Left. I'm just gonna do a couple more, just to kind of hammer it in. Which position was that, Elijah? Both, yep. Left is closed, but not right. Which position's that, Sydney?
Right.
Yeah, you guys are getting it. Did you whisper to her?
No. You think I wouldn't know how to answer?
Well, I just, he was just saying good job. He's a helpful fella, so I could, right, he's like a ventriloquist. Oh, wait, last one. John. Left. Okay, good, you guys got it. If we stop the lesson right there and that's all you got today, and nobody forgot it, we'd probably be good and you'd be ahead of most classes. I think what happens is people get a little bit past this and it gets more complicated and they start to lose pieces. So that's why I'm not gonna go into how magnetos work at this point. We're just gonna focus on the switching mechanism. But that's pretty much it. And that's why I started you out at, hey, the reality or the basic is we've got two switches, and if we get a little fancier, we got a start switch in there. So here is a drawing, and this is pretty common to how they're labeled, is we got ground here, and I cut it out so it doesn't have the rest of the drawing. But we'll figure out which one it is. So one of these would go to one mag, one of them would go to the other mag, right? So they don't necessarily label every terminal as off, left, right, both, but we're just saving ink. But we could come down here and do the same thing. Off, left, right, both. So this is what's happening inside these magneto switches. So if I move the selector from off, you noticed on off, this one is grounded. This one is grounded. So we're both off. So if I move that selector down to this position, notice the dotted line here. So that says if I move the top one, I move the bottom one. So now I'm to L. Which one of these magnetos is L? It's a little trickier question. I'll take a little guesswork. Leo, I'll ask you, and I got to figure out. So we're in the L position. The question would be, would our L mag be shorted or not shorted?
Top one, the left is not shorted.
All right, this one is not shorted because notice this terminal doesn't go anywhere. It's just hanging out in space, not connected to anything.
The left is on the top.
So left is on, so that means we're in the L position, which means we have the left magneto on. So this is the left mag, this is the right mag. Our right mag is shorted now, right? See how that works? So, that's how they work. If you try to just think through it too fast, that's where you get confused. If you go really slow and say, okay, when I set it to left mag, I want my left mag to run. If my left mag is running, the engine's the one that's powering it, so it's just making spark. If I want it to run, it's gotta be an open switch. Because if I ground it, it's not gonna do its thing anymore. Alright, so that means if we go down to this setting, to the right setting, now my left mag would be grounded through here, but my right mag, that terminal's not going anywhere, it's just hanging out in the middle of space, it's a nothing terminal. And then if we go to both settings, not plural, well, that's kind of plural. If we go to both, neither of those are connected to anything, they're just hanging out in space, not really doing anything. So on both, neither of them are grounded, they're both open switches. Tracking with me yet? Good. Alright, so when you guys are making your boards, what gets a little tricky in your head is we're used to drawing switches with the electrical power where we're allowing it to get somewhere, right? We can put a switch like our master relay so that it will allow it after the load to get to ground or not get to ground, and that's probably how you want to wire your magneto on your board. We didn't spell it out that way, so you can get creative if you want, but that's going to be the simplest way to do it. So when I draw wiring diagrams, I try to put the power on the left and the ground on the right, so that dumb people like me have their head on straight and it helps them. So if we put the ground over on this side of my wiring diagram, and I put my battery over here on this side, plus, minus, that goes to ground, right? One of you guys did that on your drawing just to kind of help you visualize. I'm okay with that. So, if we have two light bulbs, one is right mag, one is left mag, and the problem is if we want them to light up on our project, we go, okay, we got some reverse thinking. If all I did was hook them up to my mag switch, there's my common on the mag, there's my, like that, left, right. If we were to just hook them up like that, now you'd have a bus bar and a master, and I'm not going to draw all that in, right? If all we did was hook them up this way, when we have the switches in this position, which is that left, right, or both, Nathan Ziegelbauer, both. So in this position, are our light bulbs going to be lit up? We're backwards. So even though you have it set on both, the light bulbs are not lit up. And a smart aircraft mechanic would go, oh, I see what he did there. But somebody that's coming through on a SMAT tour is going to be so confused because they're going to say, how come the light bulbs aren't on? He's got it on both. So you are allowed to wire it this way in your project if you want. That's the simple version. If I was to switch those to this position, now both my light bulbs would be lit up, right? And that position is what position, Zach? Off, yeah. So a lot of you guys are going to be like, I don't like that. I want my light bulb to light up when simulating the magnetos on. So the way to do it is we're going to take a separate circuit. There. We're going to take a separate circuit, and we're going to actually put our light bulbs for the circuit, for left and right, over here. And instead of having this light up the light bulb, we're gonna say right relay coil, left relay coil. That's right contacts, left contacts. Now I don't have my master and my circuit breakers and my fuses all in there, but we want to draw something in. Normally closed, normally closed. All right, so if we wire it this way, when I have the switches set in this position, are these coils getting power right now? Nope. So if they're not getting power, that means our normally closed position contacts are closed, because they're normally closed, and my power's going through and it's lighting up my light bulbs. Oh, that's handy. So if I come over here and I switch it to, let's see, start on the left mag, I close the right mag. All right. If I switch it to that, so which position is that one? Brian?
Position is that one, that's gonna be left.
Left mag, yup, because the left mag's the one that's open. So now my right magneto is allowed to have little ants come through, which is gonna change the contacts of the right magneto coil. So now my right light bulb is gonna go out because there's no path for electricity through the right light bulb. So we're set in left position, and our left light bulb is the only one that's on. Everybody tracking with me? Cool. So if you're wondering how to wire your magneto switch, this basically is the wiring diagram to make it both the simplest and have the light bulbs make sense. If you don't want to do extra little relays, you just do the top piece. So I'm going to leave that up there for a minute, and actually we're going to do a little 5-6 minute break after I take attendance, in case some of you aren't quite getting it and you want to ask some questions. So attendance, Steven's gone. Is he the only one? That was quick attendance. Go ahead, take a little 5 minute break. I'm gonna mark that. If you got a question, come ask me.
Is there a standard way to do the lights? Meaning like
Standard would be, I'd say it's 50-50 on our students that do relays versus.
but in the real world, I don't quite get that.
In the real world, it goes to our mags. So yeah, it just goes right to the mag fill wire.
So it would be, the light would be off if it's connected.
There's no light. It goes to that component called the magneto. We're gonna go in that in depth.
I thought that when I had a light just
The relays are,
No idea. That's why we started aircraft and often we shut down. We actually check, listen to see if we have enough light change to watch the tachometer. So we'll turn it to just 1 or 2 mags, and it's not gonna go the white is good. And we go, okay, yep, that one's working. We go to the other one, yep, that one's working.
you have to go to both before you go to the other one.
We go back to both. So if I was on both and I'm running at, let's say, 1800 RPM, if I go to right, it's going to drop somewhere between 50 and 150 RPM. Most often we go back to both, put it back up, but you actually don't have to. You can just go to left, and it would basically just stay where it's at,
Okay.
right? So it stays low. And then sometimes we go all the way to off. The engine will, the engine will be like, whoa, boy, we better turn it back to low. If you wait too long at off, you're still dumping fuel in the engine, so when you go back, you can get a bow! Hit the exhaust pipe. But yeah, good question.
Okay,
Yeah.
can you explain to me how the switch is controlling the lower circuits? Because they're not connected.
Drawing on this wiring diagram, you don't see the connection.
Okay.
I'm gonna get a relay for you.
Me too.
So it'd be one.
I need some help, guys.
However,
So we could draw that this way, but it'd be a normally open contact.
Okay.
So what they do is we get a little bit fancier, and on this contact, it just has a lot more terminals for us.
Yep.
So we still have the blue as the wiring for the coil. And if you follow it really close, the one coil wire goes to this one.
Okay.
The other coil wire goes to this one. So we would hook those two up to our coil, which would be like the top of the drawing.
Okay.
Now, we've got 6 other contacts here, because basically this is a double pole, double throw. So what happens when that coil comes on, it pulls this down, and it changes, see the little contact is there? So this white wire is basically the, I hesitate to use the word common. Actually, we don't have that connector on here.
We may have to order some more,
All right,
but you're gonna show
That'll
them,
work for now.
you'll show them how you strip a chunk, strip another chunk about 1.5 inches,
you know, I probably should do
and
that.
then poof it up,
I have it on the picture.
and then open it up, okay, and then make sure the ground wire comes out the back
Back of shrink wrap.
of this, so, yeah, that you put a squeezer on it, right, and then you're fitting.
Okay,
That should be about 1.5 inches.
thanks for grabbing that for me. All right,
I'm surprised I didn't see.
so I drew this relay, right? But I drew the contacts in the middle. Now, normally, when it's sitting there, it's connected to only one side of the back side of it. So on this one, it's connected to this top one. So this wire is normally connected to this one.
Okay.
And that's what this is showing. So what you do on this wiring diagram is this terminal here would be, I don't know if it's numbered, we'll say that one, number 12.
Oh,
So this is 12,
what is this, what is this word?
and this one, the normally closed, is gonna be this top one. So, number 3 is what's printed on there. So that's a normally closed switch here, normally closed. And then the top would be the normally open set of contacts. So we're not using all the wires, so if we wired this in, we would use the coil wires for the top line. And we would use this wire and the normally closed one here. So that way when we power this thing, this is gonna say, it's gonna open. So that's what we call the difference between normally closed and normally open.
So basically, there's a switch somewhere between.
Well, a coil, that's a coil.
Okay.
Yeah.
And it spins around here. It opens that.
Yeah.
Spins, travels.
So technically, could you use a knot gate? Get the same effect?
Oh, man. I'm gonna go with no.
Is it like not, you know?
Yes,
That's computers, so that's not.
yes, technically, I guess that is a form of a NOT gate. The NOT gate's a transistor and it's basically, yeah. You know what, technically, that is a NOT gate. If you really wanted to go there. Yeah.
You did it like that? Just turn your boat off.
Say what? If I turn, if I have it this way? So if I have it this way, this switch is open, so I do not have electricity going through here. And we're using the normally closed contacts. So they're actually both gonna be on, because my power can go through. When I close them both, which is the off position on the switch, when I close them, now I have electricity going through both of them. And because I have electricity going through the coil, it's gonna switch those contact positions.
Don't you want them on though, when they're both on? Oh, those are both off.
So when it's,
Yeah, those are both off.
when it's in this position, that's actually on, circle it, that's off,
Yeah.
which means my lights will be off, yeah. It's a reverse,
Yeah.
and then it reverses
keep
twice
track.
on you.
Yeah.
What I don't get understand is what the connection here and here.
Yeah, so that's these right here. So it's a little relay. So you've got this wire and this wire are going to the coil that is gonna be turned into a magnet, okay? So that's the magnet that pulls the switch to change the position. And then these are connected to the terminals. So this terminal here would be like this one. That's the wire supplying power. And that wire is either gonna be connected to this terminal or this terminal. So we're gonna pick this normally closed, which means it's normally connected, and we're gonna use that one. On your other wiring diagrams, you would have used this switch, right, a normally open, and you say, hey, if I have power, I want it to close. But we're just using the opposite. We're gonna say if there's no power there, then I have electricity that can flow through it. But if I put power to this coil, this is gonna switch, and now this top terminal would be open, power can't go through it. You can take that to your seat and look at it. All right, welcome back. Did a little explanation to John and Abednego. If you're not quite getting what's going on, highly recommend grabbing one of these clear cubes, and you can physically look at what's going on with the contacts and go, oh, okay. And if you want, I love explaining this to people, so come grab me during lab time and we'll talk through it to make sure you're there. I'm just gonna, I don't like that one. Alright, so that is the simplest mag switch. We'll call it a mag switch, we'll call it an ignition switch, whatever you want to call the switch. That's the simplest version. When we get more complicated, it kind of builds from there, but it's doing basically the same thing. When we get to power plant class, we're going to go into these drawings, which it's the same switch, but they add one extra set of contacts again. So the ones we were just looking at were this right and this left. And notice we have one extra position now. We have off, right, left, both, and they added start. So there's one extra position that we can turn it to on the key. But the left and the right portion of it are basically doing the same thing. So if we follow the lines, our left magneto in this start position is coming down, and you would say it's going to nowhere. It's not grounded. We'll get a little bit more complicated and know where those wires are going, but we're going to save that for later. But it's not connected to ground, so it's basically going to function. But our right magneto, when it's in the start position, and like I said, you could take off, right, left, both start, and you could move them off, right, left, both, start. Notice the dotted line telling you that all the switches will move together. So the right mag, when it's in the start position, is connected to ground, which means magneto's not going to be putting out any spark for us. So we're going to go over the more complicated diagrams and how they work, but basically you're just looking at those two sections and you're ignoring some of the other terminals on here. Now that said, if they moved the start button into your start switch so that you go all the way to start, there's an additional switch inside there that's going to do something. So instead of just two switches, there's actually 1, 2, 3, and on some of them there might be 4. Ziegelbauer.
Do you want us to draw that out when we do our wiring diagrams for the
Not-
magneto switches, or just?
Not that one. You could just do the simple version that I had drawn up, which is basically this one. The one I erased. Yeah, you can have the simple version because, I mean, if you want to draw this one, you're welcome to. You're just not going to use everything that's in there. So we add one extra switch, and at one point we had one that was totally disassembled. When we get into power plant, we'll see that. but you can actually see how there's 4 switches stacked up inside of there making all these connections. It's kind of cool to look at. But that's not the point of this class quite yet. So the start switch is a totally isolated from those other switches. It happens to be in the same housing, but electrically it's not connected unless we connect wires. That start switch will take positive voltage from the battery. So there will be a bat terminal on the back of here somewhere. Your eyes are really good. It says bat right there. So it'll take positive voltage from the battery, and when the key is in the start position, it'll send that positive voltage out to the coil of our start relay. To tell the engine to run. Why would we not just send that electricity right to the starter motor, Martin? We want the motor to start. Yeah, it's kind of a thinking through. Why do we send the power to a start relay instead of straight to the motor? Why do I even have a start relay? I caught him too early in the morning. Corbin. Our starter motor might be 80 amps. These guys with those terminals, they can't handle 80 amps. This is just a tiny little switch. So that's why we use a relay, is with half an amp or whatever's going to come through these tiny little terminals, I can send half an amp through a switch that's got 5 of them lined up. And so that's the reason I use the start relay, is I can turn power on using just a half an amp through this guy with tiny wires, and then out by the starter we would have a positive off the battery to the contact portion to the motor. So we'll have half an amp or whatever. Actually the start relays are like 6 amps, right? So if you notice, if you leave them on too long they get hot. So maybe I shouldn't say half an amp, but this will take 6 amps, but it won't take the 80 amps or 40 amps or whatever the actual motor is going to start at. That'd be insane to hook up 8 wires that size to this thing. All right, everybody following me on that? Makes sense, Martin? Yep. Cool. All right, so if you're wiring yours with a magneto that has the start function built into this, that's what you're going to have to do, is you'll have it drawn kind of like me. You can use this one if you want, but the bat you'd power with hot from the battery, and the start's going to go out to your start relay to turn your little motor, or if it's a light bulb, turn your light bulb on. The back of these are printed with what terminal goes where, and I'll admit they can be a little confusing. So for instance, bat is this one, R is this guy, GR here is this guy. So you gotta kind of have an idea what's going on. It's whatever's closest to it, but you gotta be thinking about it while you're doing it. This was a drawing I had. Now, the model number switch you have may or may not make a difference, right? They might switch some stuff around on you. So I grabbed this diagram from whatever model number switch this was. They're pretty generic, fairly identical, but just be careful that it's truly that way. So I put it in here. You guys have my PowerPoints, so if you need a little bit of a review, you can pull this up and go, hey, what are they labeled and where do they go? They start trying to draw the wires and it gets busy. This R here has a ground next to it, and I want to point that out. That's not the main ground coming out of here. What happens is there's a jumper wire between our basically right ground in the start position. So if I circle this wire right there, that wire is this jumper wire. So what happens is if that jumper wire is not on there, when we go to the start position, our right magneto wouldn't be grounded because that wire I circled doesn't exist. So that's what, if there's a jumper between those two are, like on here, it is. So if you have one that you for sure want the right mag not to be illuminated in start, you may have to put that jumper on there. And we'll talk about that more in mag class, but when we start an aircraft, we typically are only starting on the left magneto, not the right magneto. Well, at least that's how we've taught for about 50 years. Now they're changing things, and we're starting to do both. But that's what that ground is, so use the main middle ground one, not that little guy that's hanging out over here. Oops. If you use the little guy that's hanging out over there, basically it would only work if the jumper's on there. Which, if the jumper's on there, you're connecting to this terminal. I'll put an A there. So A, well, it's up here. A would be I don't know if I drew that right. We'll just keep moving on. I don't want to write it up there wrong. We'll go with it's that jumper wire for now. All right, questions on that? Make sense? Kind of the terminal identification? Okay. Let's skip this one really fast. All right, wire shielding. So on our magneto switches, when the aircraft's actually running, you guys won't be dealing with this now, but when the aircraft's actually running, because when we have them in the ground position, we're short-circuiting the magneto that's trying to make power for spark, or when they're running, it's not quite short-circuiting, but it's an alternating current because the way the thing works, you get a voltage, low voltage, voltage, low voltage. So you have this pulsing in the wire that's heading to your magneto switch, and that can really mess with your radios, because every time it goes to pulse, it kind of puts off an electromagnetic field. So in order to not have that electromagnetic field interrupt all your radios and stuff in the cockpit, we use shielded wire. So this is a shielded wire. Now this one doesn't have any insulation on the outside of the shield, but it makes a good picture. So in this shielded wire, you've got a conductor that's hard to see on here, but you'd have your actual wire on the inside, and then you've got insulation, and then you've got the shield on the outside. That is what this wire here is, this white one, it's what this is. So here's the white insulation. This is the shielding that they pulled away and then reconnected to a terminal. Then you got your inside insulation connected to the actual conductor that would be sticking out of the inside of it. And that goes back to that word reluctance, right? So the shielding is made out of a material that has low reluctance, which means it says, ooh, I like magnetic flux lines. So instead of the magnetic flux line going out and back into my instruments and stuff and coming back in, it says, nope, just take that magnetic flux line and just circle right through the shield. So that's what the shield's doing, is it's giving a easy path for the magnetic flux line to just pass through so it doesn't go out into all our stuff. So one of your instructions on lab 15 is our wires that go to our mag switch. We want to make them with shielded wire, and that's simulating how they are in an actual aircraft. So what you end up doing is you cut the wire off on the end, whoop, and then you have to cut it back about 3 inches or so, and you're going to do it really carefully. You can either do it with a knife, you can do it with those fancy strippers if you're careful and start with a larger size wire, but you'll pull just the insulation off, not pull the shielding off. So if we were, I'm going to draw one picture if we're dissecting. So if that's our conductor, and then there's a layer of insulation around it, and then there's the braided shield stuff, And then there's another layer of insulation around the outside. So the first step is we just cut that insulation around the outside off. And after you have the insulation cut off the outside, that shielding is kind of like a Chinese finger trap, and you can basically push it back and it'll expand a little bit, so you can work with it. So you'll cut the insulation off around the outside, you'll push it back so you can expand it a little bit. Once you get it expanded, there's kind of two ways, well, there's probably more than two ways to do it. But one way to do it is you take a pen or a nail or something sharp, and once it's expanded, you can poke that into the shield. So basically you're poking it in between the webbing, right? And you've got it expanded out like a Chinese finger trap. So you poke your nail or something in there, and you basically just kind of work that hole bigger. And you work it big enough to where you can pull the inside wire out through that hole in the shielding you just made. Once you have the wire pulled through the hole in the shielding you just made, then you'll pull the shield back tight, and you'll crimp a ring terminal on the end of the shield and a ring terminal, well, I guess you'd have to do one more strip, right? You gotta strip the insulation off that little guy. So you'll do one on there. If you wanna make it really nice, which is what we'd like you to do, then you fold this guy back and slide a piece of heat shrink on it so that the shield comes on the back side, and you end up with those two terminals, but it's heat shrunk back across to kind of protect everything. So that's what's shown in the picture here, is I've got my conductor hooked to this terminal, and then that shielding we hook to ground. So we just give it a place to, if there's from either crosstalk or anything like that, we shield that just so if there's anything going on, it's grounded. So you'll notice on my ignition switch, the shields go to ground. There's actually 3 terminals on there, right? So shield, shield, and this other one must just go to ground on the aircraft somewhere. Making sense? Corbin?
Where do you actually need the shield? Because where you have a sealed back, you got, half inch, 3/4 inch, it's unshielded. How far does that shielding have to run before?
This is a great length, an inch or so. Part of it is if we're, and I'm gonna use the word, we're accidentally making a little magnetic field off here, right? Making a signal. If you have a little bit of a signal off a little half inch of this thing, you don't have a very big antenna that's sending out the signal. So if you got an antenna that's 4 foot long, we're gonna be sending out a stronger signal for a radio to pick it up. If we got a little half-inch long antenna, it's not going very far. So that's the way I would answer that. You wouldn't want it 6 inches back, because now I got a 6-inch long antenna to be sending out radio frequency waves. So that's why it's somewhere in that neighborhood of, we don't want it too close that it's messing up our connections, but half inch, 1 inch, somewhere in there is good.
On the other end, does the shielding run all the way to the negative?
I'm gonna say depends. Depends. Sometimes they don't have you shield both ends, and I think we talked about that in instrument class. If we shield both ends of the thing, we actually make this kind of parallel circuit in a ground circuit, and it can give us funny radio stuff that I'm not gonna talk about now. So sometimes they'll shield both ends, sometimes they'll just shield one end of it, but I'm not gonna go there today. I would say general rule, connect both ends to ground, until the wiring diagram on the aircraft says not to. On you guys' stuff, shield. Well, I don't know if it matters. Let's say shield both ends for practice.
Well, like, how far does the shielded wire have to run before you use the regular wire? Does it go all
You
the way?
could use a shielded wire for regular wire.
When do you not have to use shielded anymore?
Oh,
At what
this is because we use shielded, either if it's a radio thing that we're purposely sending out really high frequency and we don't want it to escape our wire, or the reason we use it on our magnetos is because we are basically grounding out a magneto circuit that's spinning. When we learn about magnetos, we'll see that more. But these are problematic for putting electric noise in the environment because we're grounding out a circuit. So kind of like if I was to take my wire and just start tapping it on a short circuit like this, you guys would even audibly hear the snap, 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 snap. You can imagine that if I did that, the magnetic field, building collapsing, if we were, let's say, listening with a device that picks up magnetic fields, it's going to be going every time I tap it. So we're getting rid of that tap noise.
Yeah, I know, but how much of the wire has to be shielded for it to be effective? Like at what point does it not need to be shielded anymore because it's proximity to the radio, or does it have to be shielded all the way?
Oh, the whole aircraft, yeah. If you're within 30 foot of my aircraft, you better shield it. How's that?
So it runs all the way to the magnet?
Could run anywhere, yeah. Depends on what it is. Now, most of the time, this is in the engine compartment, but it's going to be one wire. You're going to go from the magneto to the ignition switch. It's only going to be one wire anyway. Yeah. Oh, that? Well, what's AC-43 say about junction points? We don't have any. I don't think you'll ever see a connection on a magneto wire. It won't go through a Molex. It's going to be one solid wire from the magneto to the ignition switch.
It's one shielded wire.
Yep, one solid shielded wire. Yep. All right. I should have that one up. So there's the guy. It's hard to see. He's got it bent over his finger, but he's using, it's funny, a blunt nail. Basically, they don't want you to have a crazy sharp nail and poke through that inside insulation. So if you're trying to pick through getting there, they don't want it crazy sharp. They don't want you to put a hole through the inside insulation on accident and not know about it. That's the only reason they say blunt nail. But, yeah, you get the idea. What was this? Radio interference crosstalk. That's just a blown up view of what we have. There's a bunch of different sizes of this stuff, but typically it's just a really low amperage. It's not doing much, so we're usually just using a real small size of it. But blown up view, you got your conductor, insulator, shield, and the jacket. All right, this was the other one. This stuff is a coax cable, is another type of wire. And are you guys old enough to, when you have to plug in like Nintendo or something, you gotta spin the coax on the TV? So, coax cable. So coaxial cable means that the axis is the same point for both conductors. So what we have is one wire and then insulation in here and then another wire on the outside. So think of it kind of like being a shielded wire, and they'll look like that, kind of like this one, but it's a wire, insulation, another wire, and on a coax cable, a true one, I'll put insulation in here, you're going to have another layer of insulation around the outside. And if you were going to use the left-hand rule of I've got current flowing through a wire, and I'm going to draw the magnetic lines of flux around it. Let's say our power is coming this way through the wire, because I drew it as a dot. We would draw, conventional, we would draw our magnetic lines of flux going around in that direction, right? And they're going to be essentially that circle established, and there's different layers of the circle, but they're going like that. Now, if I passed electricity through this conductor, and you go, wow, it's a weird shaped one, it's a hollow conductor. I go, yeah, it's a hollow conductor, but it's still a conductor, right? It'll conduct electricity. If I'm passing the current through the same way, basically my lines of flux field, they're going to overlap on the same point. So because the left, right, up, down, whatever you want to call it, the center of access is the same point. If I pass electricity the other way through this one, it'd be going the other direction, but it's centered on each other. That would be opposed to if I have one wire and I've got another wire. If I wanted to say the power was coming at me again, out of that one, we're going to draw these magnetic lines of flux for my black wire. And if I draw the magnetic lines of flux for the purple wire, they don't line up on top of each other if it's not coaxial. And in a communication or a radio thing, that's going to really mess with us because of how radios work. So that's why we use coaxial cable when we're using communication lines to our antennas back and forth. Is basically the magnetic lines of flux, the fields, they stack right on top of each other, and they're not going to have interference, as opposed to if you ran two wires side by side. Does that simplified version of what a coax make sense to everybody? Everybody following me? Cool. So that's why we do a coax cable in the simple form. Many coax cables are also shielded. So this one, you've got the center of the coax, insulation, outside conductor of the coax, and then you actually have shield, and then what they don't show is another layer of insulation on there, and then a protector. So just because it's a shield on the outside, when you look at it, you go, well, is this a single conductor? Is this technically a coax cable where they're expecting me to use that as a conductor? So shielded wire and coax cable, they can start to kind of feel like the same thing, and it's all going to be kind of how you use it, and we'll cover that more in the next class. But we don't want you to use like the big thick coax cable. We just want you to use shielded wire. But I do need to talk about coax cable, because when you're running a coax cable, there's thick insulations, and because we want to make sure that that access stays the same point, if I were to take a coax cable and bend it really tight, you can imagine that inside, if I draw it bigger, you can imagine that inside wire might want to squish to one side or squish to the other side. I'm actually compressing all of this insulation, and I'm stretching all of that insulation, right? So whenever you're running coax cable through an aircraft, there's larger bend radiuses that they want you to follow, because if you start kinking, bending, stretching insulation, it's not good for them. And then they even go in your book to say, never kink a coax cable, because if you damage it, it's damaged. But you can't see it because it's inside of shielding and everything else. Never drop anything on it. They're worried about, it's the insulation, but they're worried about the insulation / dielectric getting damaged. You don't want to step on them. Don't bend it too sharply. Loop just means, that's another way of saying don't bend it too tight. They don't want you, if you're trying to pull the coax cable through the aircraft, a normal wire, you guys might do this and wrap it around your hand so you can get a better grip, right? Well, I just basically bent that thing tighter than a coax cable is supposed to bend. So they don't want you to pull it on that kind of angle. They don't want you to grab it like this and pull it, because basically I made too sharp of a bend radius. So if I'm pulling a coax cable, they're saying pull it in a straight line. So that's what they're saying with never pull a coax cable instead of a straight line, because when you bend it on your hand, you could bend it too tight. So basically, they're saying, you know what, be gentle. They might call coax an RF, because that's radio frequency cable. Minimum bend is 6x the diameter of the cable. They like it to be 10x. They're like 10x, 10 times, but they'll say the smallest is 6. What's the smallest bend radius? I'm going to pull it out of the, oh wow, I'm getting old. Can't quite make it. What's the smallest bend radius we would use on a normal wire? Shielded would be considered normal if it's not for radio frequency. What's the smallest bend radius that we're allowed to bend one? Micah, you remember?
Is it 4 times?
I don't think that was the number. You're close. Close. Gavin?
Wasn't it 10 unless it was coming out of it?
Very good. You got half my answer. So generally speaking, it's 10, well, and then we have all these exceptions. So if it's coming out of a bundle, they'll say we'll let you go smaller, and the typical smallers will say, okay, 6. Anybody know what the smallest ever smallest is? 3, yeah. So 3x or 3 times the diameter is the smallest, so it would be on that bend radius, take the diameter of the wire, and then the problem is you change it to a radius. It'd be nice if they just left it as diameter, right? Because then it would be, maybe it wouldn't be nice. Diameter was 10. Yeah, let's not do that. We'll just stick with what they say. So anyway, 3. The only time we can go down to 3 though, if you remember, is if I'm coming around, if I have a support on my wire to make sure that, a clamp, to make sure that it's not gonna get worse, we're not gonna have vibration, it's not putting stress on our terminal connection down here. So 3 is the tightest ever, but only if we have support on there. So a little review on that. So 4 was close, but just one off. Hey, that's all I got. All I got for today. It's only 8 o'clock. You guys got a lot of lab time. Sounds good. Questions for the group before you go? Okay. Sounds good. To lab we go. Oh, I'm gonna find more of this. We obviously have this much. I know there's a roll of it somewhere, and it disappeared. So I might disappear for 10 minutes, because I think I know where it's at, and I'll bring a whole roll back.
I got the flashing So that wasn't complicated, but we got it together, it's kind of sitting in a file. We can add it.
This one? Oh, you want the drawing? Yeah, let's see. I'm gonna make sure I got it right. Why don't I just redraw it? This one works, but it's kind of hard. So if we said bus, so we'll start at that point instead of the battery, but you know, if we had a battery plus to our master to my bus. All right. So coming out of that, we're gonna go, if we really want to be fancy, circuit breaker, and then we're gonna go normally closed to left mag light. Trying to decide if I want them to be on their own circuit breaker. We could leave it on one circuit breaker, I guess. You've got options. Normally closed, and we'll call this left relay, right relay, right mag light. Alright, so now those are the contacts, but I need to power the coil part, right? So we're gonna come to, I'll give myself a left coil, right coil. Probably should have a circuit breaker in there. So coming out of those, we're gonna have a switch. And this is gonna be our mag switch. Oops. All right. And left, right, ground. So on the back of here, that is, it's hard to see, but that's this terminal says ground. So that's the common one for the 2 switches. Then you got the L here and R. All right, so there you go. If you wanted to get really long and fancy, we've got another switch inside there. We'll draw it like that. So that's going to be our start switch. So we're going to have battery and start. Now we got it drawn kind of funny, but we'd come all the way over. I'm going to bring it back just so I'm in the middle. And that would go to our start relay coil out to ground. And then off there, you're going to go through the contacts that go to that contacts to my starter to ground.
So use it to start start means when we, this is the button.
So it could be a button if it was this,
Okay.
or it could be when I go to start here. And when I go to start here, yeah, that would. Correct. Yep, yeah, battery or bus, so start, oh, I did that backwards, I'm sorry. I labeled them backwards, so this would be that, that would be start, sorry. That makes more sense now, right? Cool? Yeah, you can take a picture of that.
I mean, they wanted to make him king.
Yeah, that's the simplified version, if you remember. This is the little bit more complicated. It's hard to see, but on that, we've got 1, 2, 3, 4, 5 positions. So 1, 2, 3, 4, 5. And that's like this, where each of these switches actually has 1, 2, 3, 4, 5 spots it can be in. So if I were to erase this, so we can actually see what's going on.
Okay, 5 because the starter is added.
Yeah, so even though on your drawing, we only have basically open or closed, the way we drew it, even on the left mag, what we really have is we have, okay, so in the off position, it's grounded. In the right position, it's grounded. In the left position, there's nothing here. Okay, not grounded. In the both position, not grounded. In the start position, not grounded. This wire goes out to a complicated thing we'll talk about later. So if you draw it on your wiring diagram just like that, I'm good with it. Where the reality is, it's actually like that, right? And we're ignoring the rest of what's going on inside.
So in this case, like once you move one here, everything will move, right?
Yeah, and I try to show you that by putting those dotted lines in. So those dotted lines are supposed to be connected. That's what they're trying to show you, so that if I move this one, it's gonna push them all up.
That will be off from this positive, right?
Yeah, yeah.
And then this one will be free.
Well, and because of the way it's drawn in here, when we're on start, the battery gets connected to our start terminal. When we're on any one of these, this wouldn't be here anymore. So our battery power is just not going anywhere.
So actually power is going from here to here.
Only,
Not
yeah,
from here to here.
correct, yeah. It's going that way.
And in this case, from here to here as well, right?
Well, these are not connected to anything. They're just inside there.
So,
But
so there's no connection from here to here.
correct. Yep. They're just a position inside there with no wires on it.
So eventually in real life not use them.
Yeah, the reason they put it on this drawing is so that you can visualize, okay, when I put it to the off position, that switch would go to there. But the reality is, there's no wire connected to that, so it's like it doesn't exist. Let me see if I can find it in here. We used to have a ignition switch that